Suppose a Blu-ray player has a maximum spin rate of 165 hertz. If the angular acceleration it is capable of is 250 radians per second squared, how many full turns would the disc make starting from rest before reaching the maximum spin rate? So I think when I look at this, that maximum spin rate I think has something to do with like a final angular velocity, and I think the initial angular velocity is equal to 0, and we're given an angular acceleration. Okay, what does that mean? Let me start by looking at that maximum spin rate, right? Because what does it mean, 165 hertz? One way of interpreting the hertz, or maybe the way of interpreting the hertz, is that that represents the number of full spins. I'm going to call it like revolutions per second. So I'm just going to say revolution per second. So full turns per second. And in that sense, if I were to say, okay, is that like an angular velocity? Can I state that omega is equal to 165 seconds to the minus 1? And my answer is no, because the angular velocity is defined based on the radian per second. And there's really 2 pi, right? 2 pi radian in one full turn. In other words, I think there's 2 pi radian per revolution. So what that means that I need to do is take that 165, multiply by 2 pi, and then that should be an angular velocity. And so I get 1036, let's say, I always want to keep a few extra sig fig here, 0.7, that's probably good enough. So 0.7, and then this really could be thought of as a radians per second, which I'm going to just switch to an inverse second. So physicists will conventionally use hertz, even though dimensionally a hertz and an inverse second are kind of the same. Hertz will always mean cycles or revolutions per second, and when you see seconds inverse, that will generally be associated with a radians per second, which can then be associated with an angular velocity omega. Now we already said, because I'm kind of developing some clues here as to how to do this question, right? In that sense, maybe I'm in the first stages of solving this problem because I haven't quite figured it out yet. But we did say starting from rest, so I can write that, right? We've definitely got an alpha is equal to 250 radians per second squared. Okay, because this feels like some kind of rotational kinematics question, right? And wouldn't it be neat if one of the rotational kinematic formulas would work for this? And if I had them all written down, that might help me some more, but I don't right now. It asks for how many full turns. Well, I think that if I knew what the angular displacement was, I would probably be able to use that to figure out how many full turns. Maybe, that would be in radians, right? So maybe I could take that and divide by 2 pi, and that would be the number of full turns, right? Well, when I look at, okay, I've got omega, omega naught, alpha, delta, theta. There's no time here, right? So timeless formula. And if I think about, like, normally linear timeless formula would be like v squared equals v naught squared plus 2a delta x. But we have, instead of v, we got omega. Instead of v naught, we got omega naught. Instead of acceleration, we've got alpha for angular acceleration. And instead of delta x for displacement, we have angular displacement delta theta. In other words, the formula that I think will do the job for me is this one. Again, kind of the rotational timeless formula, I'd like to call it. So, okay. I think that gives me something to do here. I can get rid of this one as a 0. I like to do that first because it makes things look simpler. And, so that means that omega squared is equal to 2 alpha delta theta. So if I just divide both sides by 2 alpha, I think I would get omega squared over 2 alpha. And then I could take all the numbers that I have here, maybe the 1036.7 radians per second squared divided by 2 multiplied by the 250 radians per second squared. And out of that, my calculator calculates like a 2,000. Let's see, let's round it off to 2,149.6. Do I need any units for this? Well, this is an angle, so this, you could write radians, but I'm not going to bother to, because the way I look at it is, in physics, the physical angular measure really always is kind of by default the radian. If you write degree, you should put that degree symbol, but that really is actually a different physical quantity. It's a different measure of angle. Angles are a little weird to think about in that sense, but since there's no dimensions attached to the kind of physical definition of an angle in terms of its ratio of arc length to radius, the way the radian is kind of defined, that means that I don't need to really write anything here. But now if I take that number and divide it by 2 pi, so I'm going to say, take this 2,149.6 and divide that by 2 pi, right? Do that in my calculator. I wrote that maybe in a very elementary looking fashion there. But we can all enter that into our calculators, and I get like 342.1, etc. But I think that makes me confident that there's going to be at least a full 342, because it's like 342 plus a tiny bit, right? So definitely when it says how many full turns will the disk make starting from rest before reaching the maximum spin rate, I think it's going to complete 342, and then somewhere between that and 343, it reaches that maximum spin rate, actually closer to 342. It's pretty darn close. So that's my answer, 342.